Welcome to today's Explainer. We've got something truly spectacular to look at today. Just picture this scene for a second. You're looking down at a beautiful, dark walnut workbench, and sitting perfectly still right in front of you is this compact, totally unassuming metal oval. Honestly, it just looks like a simple mechanical toy. But what's about to happen on that workbench? Well, it's a brilliant demonstration of exactly how precision engineering works. We're going to break down this incredibly intricate physical transformation, diving right into the raw mechanics that make the seemingly impossible look absolutely natural. So that brings us to the ultimate question, doesn't it? How exactly does a compact little metal oval become an 8-legged predator in just a matter of seconds? And we're talking zero movie magic here. What we're looking at is a flawless demonstration of sheer logic and mechanical design. There's no trick photography, no CGI. The real beauty of this explainer is that it reveals the fascinating logic behind precision mechanics, proving that with exact tolerances and some seriously clever spatial design, a completely inanimate object can seem to just come alive right before our eyes. Section 1. The Uninterrupted Metamorphosis. Okay, let's dive into this. The action kicks right off from a super intimate first-person perspective. You see a thumb press down on this clearly visible amber button, and it releases this incredibly satisfying metallic click. That click, that's the catalyst for everything that happens next. A single, uninterrupted take, no cuts, no camera jumps. And honestly, what truly elevates this whole demonstration is the cinematic realism of how it's captured. It's all happening in one continuous shot, no cuts, absolutely no camera jumps to hide any mechanical flaws or hiccups. The camera is just fixed steadily right there on the workbench. Almost instantly, you see these precision locking pins retract, and that layered oval shell actually begins to separate along these incredibly tight, pre-existing panel seams. It creates this continuous, uninterrupted momentum that literally forces us to trust the physical engineering we're witnessing. Section 2. Mastering Volume and Space. As those initial pins retract, we get treated to a truly brilliant display of volume conservation, comparing the compact oval shell to the articulated Scorpion chassis. So multiple armor plates start rotating outward on these completely concealed hinges, right? This makes room for the internal mechanisms to breathe and expand, but without adding any physical mass whatsoever. It perfectly illustrates the stark contrast between that original compact shell and the massive articulated Scorpion chassis it's turning into. As those armor plates fold away, the internal chassis actually rises up slightly through these nested structural supports. But here is the really fascinating part. It remains completely consistent with the original toy's volume. There are no extra pieces magically appearing out of nowhere. Every single component that's now rising and expanding was perfectly folded and contained within that tiny original space. The hidden anatomy features brass gears, rotating drive shafts, cams, miniature flywheels, and springs. Beneath that rising shell, a dense network of interlocking metallic components is suddenly exposed. And wow, it is breathtaking. We are essentially looking at the hidden anatomy of this machine. You've got brass gears meshing flawlessly together, rotating drive shafts, transferring power, miniature flywheels, and tension springs. And this isn't just aesthetic. This is the literal engine of the metamorphosis. The sheer density of these parts, packed so perfectly together, really shows you just how incredibly exact the tolerances have to be for this whole mechanism to function without jamming up. Section 3. Articulation, legs and claws. Now let's take a closer look at how this machine actually deploys its appendages.
The deployment happens in 4 steps. 1. Unfold from nested position. 2. Telescope outward section by section. 3. Rotate downward. And 4. Lock securely into stance. Watching this from beneath the expanding shell, 8 segmented legs begin to deploy in this beautifully choreographed sequence. Let's break it down. First, every single leg originates from a really carefully folded nested position. Second, they telescope outward, extending section by section through multiple articulated joints. Third, once they're fully extended, they smoothly rotate downward. And finally, they lock securely right into a stable walking position. It's this beautiful cycle of continuous mechanical tension pushing the leg out, followed by a crisp release that permanently stabilizes that walking stance.
Crisp mechanical clicks confirm full engagement. As those legs find their footing, you hear these crisp mechanical clicks confirming full engagement across the entire chassis. Right at that same moment, the front housing divides symmetrically. And from this newly open space, 2 articulated pincers extend forward on precision sliding rails. Now, these aren't just solid, clunky blocks. Layered mechanical plates rotate and unfold into highly detailed claw assemblies. And just to prove they're fully engaged, each pincer slowly opens and closes exactly once. It's a very deliberate, almost theatrical, mechanical confirmation that the front assembly is locked, loaded, and ready. Section 4. Telescoping the scorpion tail. Let's shift our focus to the rear of the device, because this is where the spatial engineering gets truly aggressive. Telescoping rails are nested mechanical sections that slide outward from within one another to drastically expand reach from a confined space. The shell at the back separates into progressively smaller segments, which sets the stage for what will obviously become the scorpion's most iconic feature. The real secret to this tail is the use of telescoping guide rails. In case you aren't familiar, telescoping rails are nested mechanical sections that slide outward from within one another. It's a genius way for an engineer to drastically expand the reach of a component from an incredibly confined space. In this specific scorpion, each tail section seamlessly unfolds from inside the previous one, using rotating hinges and these sliding rails to stretch way out, far beyond the original footprint of that little oval toy. The tail deployment. 1. Shell segments separate. 2. Sections telescope outward. 3. Tail arches upward gracefully. 4. Final stinger rotates and locks. The graceful, multi-jointed movement happening here is just stunning. First off, the rear shell segments separate. Second, the sections telescope outward to reach their full length. Third, relying on those precision hinges we mentioned, the entire tail arches gracefully upward right over the main body. And fourth, to perfectly culminate this sequence, the final stinger assembly rotates directly into position. It manages to remain compact and perfectly proportionate to the rest of the body, completely matching the visual and engineering style of the entire machine. Clean metallic click. When that final stinger locks into place, there is a clean metallic click. Just take a second and mentally hear that highly satisfying auditory cue. That is the unmistakable sound of perfect tolerances meeting. It signals that the tail's perfectly engineered lock has fully engaged, meaning the physical transformation of the body is officially complete. Section 5. Powering the transformation. So we've seen the metamorphosis itself, but how on earth is it powered so smoothly without any pauses or hesitations? Synchronized cams are rotating mechanical links shaped to convert continuous circular motion into perfectly timed, precise linear movements. Throughout this entire sequence, every single movement we've seen is driven by those visible gear trains, rotating shafts, and telescoping rails we touched on earlier. But the absolutely crucial point here is the use of synchronized cams. A cam is essentially a rotating mechanical link, and it's shaped very specifically to convert continuous circular motion into perfectly timed, precise linear movements. By pairing these synchronized cams with the gear trains, the engineers can flawlessly coordinate the timing of the entire physical metamorphosis. The cams are what ensure the legs don't deploy until the shell is safely out of the way, and that the tail doesn't strike until the base is completely stable. It is, quite literally, mechanical programming. Component versus action. Springs compress and release naturally, while brass gears maintain rhythmic rotation beneath transparent windows. When we break down how the power transmission actually works, you can really see how physical believability is maintained throughout the whole process. The springs compress and release naturally, and that provides the raw kinetic energy required to push those heavy brass components outward. Meanwhile, the brass gears keep up a rhythmic rotation, which you can actually watch happening right beneath these little transparent inspection windows on the toy's casing. The power just flows continuously through the system, maintaining an uninterrupted, almost lifelike physical flow. Section 6. The final stance. At this point, the mechanical scorpion doesn't just stop moving, it settles. It makes these very subtle balancing adjustments until it locks into a perfectly stable, predatory stance. Premium craftsmanship involves smooth precision movements, fine machining marks, and polished surfaces highlighted by warm light. This subtle settling really highlights the beautifully polished surfaces, the fine machining marks, and the incredibly smooth precision movements all brought out by the warm light of the workbench. And why does all this matter? Well, because this foundational precision engineering, the exact tolerances, the material strength, the absolute mastery of physical space is the exact same foundational logic that drives the modern hardware technology we rely on every single day. From the friction hinges on our laptops to the complex internal mechanics of aerospace robotics, it all relies on this exact level of physical problem solving. In a world entirely obsessed with digital software, isn't there something profoundly more beautiful about raw, perfectly synchronized physical mechanics? Which leads me to this final thought. In a world that is so heavily obsessed with digital software, cloud computing, and virtual code, isn't there something profoundly more beautiful about raw, perfectly synchronized physical mechanics? Seeing gears mesh and metal unfold right before our eyes, it really grounds us in the physical reality of how things actually work. I hope this explainer has left you as fascinated by physical engineering as I am and totally eager to explore the mechanical marvels hiding in the world around us. Thanks so much for joining me, and keep questioning how the world is built.